maybe I have somebody. Nope, never mind. It just made it sound like someone was coming in and no one came in. Oh, okay, back to the whiteboard. Okay, so y equals 20 over 1 plus x squared, and y equals 2. I mean, my guess, even though I haven't actually graphed this yet, is that when you graph this, it probably looks something like, when you're at 0, it's up here at, like it's way up here at 20. So does this thing look something like this and then look something like this?
Yeah.
And so were you able to find the points where they intersect?
Yeah, they were actually pretty clear on the graph. I think it's just like 3 and -3.
Oh, nice.
Yeah.
And actually, here's, I guess I could double check it, but I would definitely do it on the graph just to save yourself time. Is you could set these equal to each other, and if I move this over here and divide, it's 1 plus x squared. Yeah, equals 10, and then x squared equals 9, and then you square root and get 3 and then perfect. Yeah. So then to find the area of this thing for part A, it'd just be the integral from -3 to 3 of the top.
Oh.
Minus.
I was thinking that it wanted like the other part, the outside parts. So I was like, wait, how do you do 3 to infinity?
Yeah, it wants this, yeah, it wants all that, the guy. So yeah, type that in just so that we can put that down, whatever that is.
$37.96.
Yeah, I wouldn't guess that it would be nice, so I'm gonna go with it. No one's here to verify us though, so we could be good. Actually, I might have the answer key somewhere. Maybe I'll go get that just so I will talk about the next one so you can plug it in while I try to go find that. So now it says let's just revolve it about the x-axis. So we're just going to revolve this. So this is where I might, redraw it under here. It looks something like this, and it's going around. Is this like a washer method, or is this just like a pi r squared minus pi r squared, or is this just a pi r squared? What are you thinking?
This would be like a washer.
Yeah. So we're gonna have to do the integral from -3 to 3 of pi r squared minus pi r squared. But then what's each of the radiuses here?
The first one's gonna be the top curve. Second one's just gonna be the 2.
Right. And so then you just have a ton to type into Nint on that one. And while you type that in, I'll see if I have an answer key. I won't have one tomorrow because today I'm going into my classroom and packing up all of the things. But I could probably take a picture of the answer key to have it just in case. I might do that. Here it is. Yep, that's what I got.
871.2.
1,871.2?
Yep.
Yep, that's what I got. Booyah. Okay. 1,871.2. Okay, part C is definitely the hard part. Because this is where you're still dealing with the same shape. There's a line at 2, and then there's this big thing that comes, and it's at 3 and -3. But they're saying for this solid, the cross sections perpendicular to the axis are semicircles. So that means like coming off of this thing are like semicircles. Which this is where we're going to have to integrate from our bounds still. We're like good there. but all we have to do is we have to do the area of a semicircle, right? That's what we got to put in there, because once we integrate that, we'll have volume, right? They want to know the volume, but we got to put the area in there because then the last dimension is taken care of. So what is the formula for the area of a semicircle?
Well, a circle is pi r squared.
Perfect. And then
So,
you would just take half times that, right?
okay.
So that's nice enough. So it's just half pi r squared, so that's perfect. So it's 1/2 pi, and then the main thing is we just have to figure out what the heck the radius is. And that is a really, really hard part of this one. Because a radius in my picture, I would have to draw it from here to here, right? Or I could draw it from here to here. I mean, either way. It's way more handy to think of the diameter first, though, because isn't the diameter from the one curve to the other
It's
curve?
the whole thing.
Right. So the diameter is just, we've done this a lot, it's just the first curve minus the second curve.
And then
Right.
divided by 2.
Yeah. So this is what has to go in there. So, like, if you can type that in super nicely, feel free. I think what I did when I was doing this, that's an X, is I think I went ahead and pulled the 1/2 pi out so I can multiply that by it at the end. And then I squared the top separately from the bottom, because 2 squared is 4, right? And that's really easy to just have on the bottom, it's 4. And then I pulled that out too and made it 1/8. So then all I had to plug in was just this thing squared, which was a lot easier to deal with, just doing that thing squared. But
Well, when I plugged in like the whole nasty thing, I got 174.3.
That's what I got. Great. So yeah, if you don't want it, if you just want to plug it in like it is right here and you're like, I can do that and I feel good about it, then don't mess with it. So. How do you feel about that one now?
Good. Now that I actually know I was just looking at the wrong section.
Yeah, that's helpful. And I think the only really tricky part of this one was part C, really. So that one's I think totally fair game for everyone. So Marissa and Chloe, totally fair game. Number 2 does have a really tricky last one, not gonna lie. But we can do this. Okay. Number 2. Large graph. The amount of water in a storage tank in gallons is modeled by a continuous function on the time interval 0 to 7, which is measured in hours. So obviously that's the curve thing, right? I don't know what this line is yet that jumps, right? But we know the curve thing is what this is talking about because the line thing is not continuous. So it says the rate at which water enters the tank is this crazy function 100 t squared sine root t gallons per hour for 0 to 7. The rate at which water leaves the tank is 250 for 0 to 3 and 2000 for 3 to 7. And that's that line that jumps. So I'm guessing that that other function is the entering function. That'd be my guess. Oh, that's really nice. Okay, it does say the graphs of f and g, which intersect at t equals 1.16. So that's their first crossing point right in between 1 and 2. So feel free to look on. And t equals 5.076, right around 5 near the top. At time 0, the amount of water in the tank is 5,000 gallons. So that's really helpful to know because it's at 5,000 gallons, but then there's going to be some filling, but some emptying that goes on, etc.
But on the graph at 0, it's at 0.
Right, and I think that's because, yeah, so this is kind of tough to wrap your brain around because the graph is giving like essentially, since this graph has gallons per hour over here, this is technically a velocity graph, but in terms of gallons. So it's, if it had been at like, if it's a quote unquote position graph, then it would have to start at 5,000 because you'd be like, oh, we've got 5,000 in the tank right now, and then it drops or it grows or whatever. But right now, what I'm saying is it's like, we just have one, and I don't, we're gonna have to see, there might be a question or two that maybe involves the graph, but right now, the graph is just showing like two separate functions. This function is the water leaving, and then this function is the water coming in. So I guess right now, I guess to wrap our heads around it, so that's a really good question. I'm glad that you kind of posed that, because it's like, well, why is that? I think what it's trying to get you to do is be like, okay, it starts at 5,000, but for this little bit, it's kind of interesting to note that it's leaving quicker than it's entering, right? Just because the red's above the blue.
Mm-hmm.
And so that might be a good, I think that might be the main thing to wrap our head around right now to start, is be like, okay, for this little period of time, it's leaving quicker than it's entering. And actually, what do we know about like total distance and total area and total things like that? Like they're all kind of the same. So I think if we were able to like find some area there, we'd actually be able to find how much water it lost. But then here, if you notice, the blue line's above the red. So what's that mean?
Would that be like it filling again?
Right. I think it would be going up again then. Exactly, because the blue would be going faster. And then in this area, again, it's, in this area again, it's draining faster than it's filling, right? And then here it's filling faster than it's draining. So I think it's kind of, I think that's probably the main thing to wrap your head around to start, is to be like, what is actually going on? But part A is actually not as scary as you might think, because it just says how many gallons of water enter the tank during the time 0 to 7. So that doesn't ask anything about anything leaving. It's just talking about entering. And so it doesn't matter if things are leaving faster or doing anything faster, it just wants entering. So how can we find how many gallons of water enter the tank? And my hint is that's total gallons.
So we're trying to find the total gallons of water that entered.
Yeah.
So would we use the two curves that have the blue on top?
No, because here it's not even worried about things that are draining. So we actually just want to look at the blue curve. We don't even care about the red curves, because it's like, well, after it enters, who cares how fast it's draining? It just wants to know how much is put in those 7 hours. So how do we typically find a total of something?
You take the integral of it.
And so we just take the integral of, and what are we going to, which function is the one that maps the entering?
That matches, oh, so it would be the 100 r squared sine.
Yeah.
Square root. Maybe from 1 to 7 or 0 to 7.
Yep, perfect. So that's all they want you to do for part A, actually. And then it just does say round it to the nearest gallon. So instead of doing point something.
Okay. $8,263. Oh wait, 264.
Yep, got it. Perfect. And actually, we kind of did talk through part B already. So I mean, that's one hint that you can just use when you're doing these, is if you don't understand how to do a part to start, feel free to just read through all the parts, because that can give you a hint of maybe what you're supposed to be looking for. Because part B says, find the time intervals during which the amount of water in the tank is decreasing. So that would mean that more water is leaving than coming in, right? Which we've kind of already talked about. So that can kind of give you a hint. So where would we say that when is the water in the tank decreasing?
Oh, when it's decreasing,
Right.
wouldn't it be where it intersects or?
Intersects is right. That the intersection is actually at that sweet spot where it's draining and entering at the same time, at the same rate. Right. So the water level wouldn't be decreasing or increasing there. It'd actually stay the same for that split second. So thinking through kind of how we already talked about the graph, what sections of the graph would be where the water level is decreasing?
The sections of the straight lines or the horizontal lines. Not vertical.
So this goes back to our question of, like, we mentioned in this area, what did we say was happening?
It was decreasing.
Right. See, that's what I'm talking about. So in this area, does that make sense? So it's going to be like, and so that would be like part of our answer for part B would be this, because if it's draining faster than it's coming in, from 0 to 1.6 would be a spot where it's decreasing. And this is time. This is a time interval. Where else is it going to be decreasing?
The wouldn't it be 1.6 to looks like 5?
Not 1.65, because this would be in here, and that's not decreasing, right? But I do agree with you that this is decreasing. So from where to where is this part?
Yeah. Oh, 3.
Yeah, so also from 3, and that this is like the 5, and they actually give you these. I probably should be more specific and actually say 1.617, because they give you that, and 3 to 5.076. Like, I should probably use all of those because they tell you that. So why is that true again? So why do we know that the water level is decreasing there?
How do we know?
Yeah, how could we explain that?
Not using the graph. Because if you're using the graph, just be like, well, this line's above the other one, so it means decreasing faster. But
right, and I think you could still just use that, but without referencing the graph. Just put something like the draining rate exceeds the entering rate in these places. Or I guess we should say maybe intervals is a more specific word. And I mean, because the reason is they kind of give you the graph, but they also give you the function. So you could, I mean, you very easily could just go start plugging points in. And they told you that where they meet, right? Since they told you where they meet, then I would say you don't even have to reference the graph. You could be like, you can just plug in points in between, you know, where they meet and where the thing jumps and know where that is. All right, this one is crazy, in my opinion. Because in part C, it says, during this time, when does the water in the tank get to be the greatest? Between 0 and 7. So, I mean, we do know a little bit. We know that it wouldn't be in here, right? Because we've already said it starts with 5,000 and it would go down a little bit, right? But then it would go up a little bit, but then it would go down a lot, but then it would go up a lot. But I don't really know if 7 would be where it is the greatest, right? So the main thing is, how in the world do we find a maximum usually?
isn't it we take, it's either like the antiderivative or the derivative and then set it equal to 0?
Yes, we take the derivative and set it equal to 0. Now the tricky thing is this already is somewhat the derivative. so that's what gets tricky, is because, yeah, we have to think through. So this is tricky. So the main thing is like, what would we be taking the derivative of? I mean, one thing that we could do is also just do some computing, right? We know that at time t equals 0, that it's got 5,000 gallons. And then could we figure out how many gallons it has at, actually, why don't we figure this out? Can we figure out how many gallons it has at 1.167 when they intersect?
It looks like it's right at half, like halfway in between 0 and 500.
Right, but that's just its draining rate.
Oh.
That's how fast it's draining. And the other one is doing this. So I think what we would need to do is we would need to take 5,000, but then add on to it well, you could really do this in 2 different ways, which is really interesting. But yeah, I've got 2 different ways. Before I kind of go into one and see what you think, any thoughts?
No, not really.
Okay, because you can kind of do this in 2 different ways. We could actually find areas in between curves, right, if we wanted. So if I go back and reference what we had here, how could we find this first yellow block? How could we find that?
You just do the integral of the top minus the bottom.
Yeah, so the integral of from 0 to 1.167 of the 250 minus the big 100 t squared minus sine root t thing. And that would basically give us how much water we're losing, right? Because remember, every time you integrate, you're getting like a total amount of gallons. So why don't we do that really quick and just see what, oh, I'm so sorry, I lost it. Why don't we do that quick and see what we get here. So let's just integrate from 0 to 167 of the 250 minus that big ugly function. And then just tell me what you get. And it should be negative because it should go down.
It didn't come out negative.
Oh, hang on. I bet that's because, oh, that's because that's on top. What did it come out as?
280.8.
Let's just go with it for a minute. Now let's take, theoretically, this should be how much it lost. Let's see if the computations make sense with what we got here. Now let's go from 1.167 to 3, right? Because that's where, and then we're going to do this one minus the 250, right? Because that's on top. Actually, I think since we kept the top curve on top, it isn't going to be negative. So that actually makes sense. My bad. Now, if you notice, your description was right. You were like, to find a maximum, we set the derivative equal to 0. And that's not what we're doing. We're actually finding it the old school way by just plugging in values and trying to find out where that happens. And I think that's the easier way to do it because there's two different functions and you could subtract them, but since different ones are on top of different ones at different times, it gets a little sticky. What'd you get for that one?
Typing it in.
Oh, no problem.
$407.4.
Now let's make sure this makes sense. So take the 5,000 that you start with, subtract off the 280.8, and then add the 407.4, right? Because it's going to lose and then it's going to gain. And then let's see if we're at what I think we should be, which is 5,126.6-ish.
That's it.
Okay, great. So I did it a different way, but this way totally works. So either way is fine. So that means we knew from our graph here that we weren't going to that we knew that it was going to go down, right? During that first yellow spot, and then it was going to go up. So we could have done this in two different sections and said, oh, if you take 5,000 minus 280, you're going to be at like 4,000, 700 and something. So it goes down, so that's not a maximum, but then it goes back up and then we're right here, right? And then it starts going down again. So that's where you can take the integral from 3 to 5.076 and figure out how much it lost, right? Which would, now this time, what's actually on top this time? The 100t squared sine root t is actually on bottom. But if you look at your graph, what's actually on top between 3 and 5?
The, oh, would it be the 2,000, not 250?
Yeah, exactly. So you could type this in and we're going to figure out what we have to subtract again. And then we're going to have to set up one more integral, which is the integral from 5.076 to 7, and the 100t squared root t, sine root t, minus the 2,000 will be this integral. And so then it's going to go up and down, and then it's going to go up again. And if we end higher than 5,126.6, that means that the max happens at the very end. If we end lower than that, that means that the max happened at time t equals 3 that we just had.
Yeah. So that's my 3. So the 3 to 5.076 was 1,109.7.
Oh, so yeah, that lost a lot. My guess is that our max is going to be at 3 because that lost a lot.
And then the next one is 496.9.
So that right there, even we don't even have to calculate the rest of it if we don't want to. I mean, we might do that just for the justification, right? So that you could add those together and get this. And so we found out, I'll just put our answer up here. We found out that the max was at t equals 3 hours. How would we justify that, do you think?
Because after you found the increase and decrease from the first interval to the next one, it was higher in the first one.
Yeah, I think that's a great way to explain it. Yeah, you could just put used integrals to calculate total gallon loss and gain. And the largest gallon amount was at that. And again, it would be great if you could be like, I set the derivative equal to 0. But the main question is the derivative of the function.
Mm-hmm. So,
because I think you'd still have to be taking the derivative of a piecewise function, even if you pieced it together. That's gross. All right, number 3. Number 3 is most unlike something that we like have not seen yet. So, because I was like, you guys have seen almost everything, and I was, even though we're going to answer this in a very similar way to some other ones, you have not necessarily seen all of this before. So, I'm probably not going to draw the chart, so I'm just going to let you look at it. So it says the functions f and g are differentiable, which is important because if you can't take the derivative of them, then the chart is a moot point. The chart and it gives you selected values here. The table above gives first derivatives. Also, the function h, so this might end up being important later, because the table gives you f and g, but it's telling you that h is actually f of g of x minus 6. So that's gross. Ooh, yeah, these are good questions because I'm going to tell you that, especially for A and B, where it says explain why, this is where you're probably going to be using the MVT, the IVT, or the EVT. So just kind of as an FYI. So it says explain why there must be a value R between 1 and 3, where h of R is equal to -5. Well, I think the first thing you got to do is we actually have to find what h of R is at these points, right? If these are the endpoints, then we can use the MVT, the IVT, or the EVT to talk about what's going on in the middle. But until we actually find, because we only know what f and g are at those things. So do you remember how to plug 1 into something like this?
So you find g of x of 1.
Right.
Then put that in, and then you find f of x of that, or f of whatever.
Perfect. Yeah.
Minus 6.
Good. Nice. So if you remember that, then you're gonna be soaring on these. That's a good. That's like a main skill you gotta have. So g of 1 is 2. Does that look good to you?
G of 1, yeah.
And then f of 2, because you have to do f of whatever that is. F of 2
9.
is 9. And then you have to take 9 minus 6.
So just be 3.
3. So basically we just found what h of 1 is because we plugged 1 into that function. Now we're going to go plug 3 into this function. So g of 3
It's 4.
4, and then f of 4
-1.
-1, and then -1 minus 6
-7.
-7. Nice. So h of 3 is -7. So we just plugged in 1 and got 3. We just plugged in 3 and got -7. And it's saying in between here, h is -5. So they're saying, could you explain why that must be true? Well, which of these theorems, kind of think back to the EVT, the IVT, and the MVT. EVT is saying extreme, so it's saying there's got to be a max or a min somewhere in between 1 and 3. The IVT is saying intermediate. It says every value in between the y values must exist. And then the MVT is saying that there must be a slope that matches the slope of the endpoints. Well, first of all, is there anything in this question about slopes?
No.
No, so it's not the MVT. Is there anything, well, actually then, so between those, would it be IVT or EVT? Is this thing talking about max or mins, or maybe something in between?
In between.
Yeah, so basically to explain this, you could just even say something like, by the IVT, -5, h of r equals -5 at some point, because every value in between -7 and 3 must exist. So that makes sense why it was so important to plug those things in.
Mm-hmm.
Yeah. And now we're on to what's next. It says part B. Explain why there must be a value in between 1 and 3 for C. I think they just use different letters so that they can, you know, make sure they're feeling good. H prime of C equals -5. Boom. As soon as you see H prime of C, what should you be thinking?
H prime of C, that's a derivative.
Right, so I'm thinking derivative. So first of all, I'm going to be like, crap, I've got to take the derivative of this function that's up here, right? So that's going to be a little intense. But the second thing I should be thinking is, of the EVT, IVT, MVT, which of them has to do with derivatives?
Be the EVT.
No, because it has to do with max and mins.
Oh. IVT is the in between.
Yep.
Oh, it would be MVT because of the slope.
Yes, so the slopes are going to match. So since it has to do with slopes, so I'm pretty confident that this one, our defense is going to be the MVT, but we're still going to have to do what we did for part A first and take the derivative of H and then plug 1 and 3 in. So here's the killer question. What is the derivative of H? So if I take the derivative of this formula up here, what's the derivative of f of g of x? Because we've done that a lot, but not for a while.
Oh, that's it's got a certain like formula to it that you do certain, what is it?
It's f prime with what's still on the inside.
The g of x.
And then you attach the derivative of the inside.
Oh.
Which is
G of prime of x.
Yes. And then the -6 goes away. So that's nice.
Mm-hmm.
So now I have to plug in 1 and 3 to this thing.
Okay. So g of x of 1 is 2. F prime of 2 is 2. So 2 times, right, 2 times g prime of 1, which is 5.
So that's
So
10?
Yep.
Actually, this is really interesting. You could have done this 2 different ways, but let's keep going with this because this is just good practice of taking a derivative.
So 3, g of 3 is 2, f prime of 2 is 2, and then g prime of 3 is 2, so it'd be 4.
Oh, that doesn't work out for us. Let me double check that one more time, just in case. So when you plug in 3, G3 is 4, f prime of 4 is 3, and g prime of 3 is 2. I get 6, but that actually still doesn't help us. Did I do something wrong? f prime of 3 is -4. Oh, wait, no, you have to take g of 3 first. G of 3 is 4. F prime of 4 is 3 times g prime of 3, which is 7,
G prime of 3,
which is 2. Never mind.
so it'd be 6. I don't know
Yeah.
where I did my math wrong.
Well, actually, you know what's funny is I just kind of led us down a rabbit trail. That was really good practice, though, because they might have you do that in some other sense. Because now that I'm looking at this, I'm like, hang on. -5 isn't between these slopes, right? Because we need to show that this slope is here. So that adventure did not help us. But the MVT does still help us. So I'm actually going to erase that, but it was good. I think it was good practice to do, because if you ever end up there, then you're like, well, that wasn't in between there. That's not helpful. What we actually have to, the other easiest way to do it is, since we know we were going to use the MVT, we steal these points that we had from part 1. So are you good with the 0.13 and the 0.3 -7?
Mm-hmm.
What's the slope between those?
It would be -7 minus 3 over 3 minus 1. So -10 over 2 would be -5.
Boom. So do you see how we got where we wanted?
Yeah.
Now we can say by the MVT, slope of the endpoints is -5. So the slope inside must match. So yeah, finding the derivative actually did not help us, which is so sad. Now we found the slope of the endpoints, which is still finding kind of like an average, slope or derivative, but boom. All right, here we go. Next one, part C. Let W be given by the integral of 1 to g of x, f of t dt. Find the value of W prime of 3. Oh man, that's crazy. Because prime means derivative, right?
Mm-hmm.
But what happens if you take the derivative? Because they're saying take the derivative of this. What happens if you take the derivative of the integral?
The integral goes away. You just have the f of t.
Right, but remember, you've got to plug in whatever this is.
Yeah, that's what I was thinking about. I wasn't sure.
You got to plug in f, and you got to plug in the g, and then what do you actually have to attach still?
Would it be the derivative of the inside?
Yes. So actually, we just got practice, even though we weren't supposed to do part B. This isn't the exact same formula because we don't have f prime of g, because the derivative of the integral took away the integral, so we don't need the prime there. This is almost the same formula, but not quite as the one we were practicing with. So we just got practice. So now plug 3 into this guy, and then we're going to have our answer for C. So as long as you know how to do that plugging in of the g of x to f and attach the derivative, then you're going to be okay. So
G of x of 3 is 4. Then f of 4 is -1. Then g prime of x of 3 is 2, so it'd be -2.
right. Loving it. Feeling good about that?
Yeah.
Cool. And then part B, this is the thing where I highly doubt again that they're going to put this on the test, because it's such a small thing, but it is good to see one of them. This is that inverse formula that's on your formula sheet somewhere. So
I have that sheet right here.
we're going to have to find that somewhere. I might even go to a new
Oh,
page.
I found it.
So it's like g inverse of x, that derivative equals what?
So this is just an f, but 1 over, well, I don't know if this is the right one. It just says 4 inverses, and then it has a formula.
Yeah, yep,
And
that's the one.
it says f prime to the -1 of x equals 1 over f prime, parentheses, f inverse x.
Ah, good. So then I'm just going to replace these with g's. Okay. This is the equation. Is that cool?
Yeah.
So this is from the formula sheet, and I would just have that. And that the reason I know we're going to use that is because at part B, the directions say, write an equation for the tangent line of the graph of g inverse at x equals 2. So without this formula, you'd be in a pickle. But with this formula, how do we write the equation of a tangent line again? What do we do?
Oh gosh, tangent line. It's the easiest thing, but I forgot it.
So we need two things. What do we need?
Point and slope.
Boom. So we need a point. And actually, don't we have part of the point?
We have 2.
Boom. So we're
Just
going to need
plug
the point.
2 in.
Plug 2 into what?
The g inverse of x.
Right. So that's going to be a little bit tricky because we have to figure out how to do that in the chart. We got to figure out how to go backwards in the chart, but that's what's going to happen. And then we're going to need a slope, which means we're going to plug 2 into the derivative of this. That's why we need the formula. If we plug 2 into this, we're going to have the slope.
Okay.
Is that okay? So that's why we need that formula. Like I said, I highly, highly, highly doubt that this question is going to be on the AP test this year because it's such a vague thing, and I'm assuming they're going to hit more of the basics. Like question number 1 on this thing, we've now seen 2 area ones. Like I would hope that they would put one of those on there. That seems mighty important. Okay, so the question is, how do we go, let's find the point first. How do we go backwards in the chart? How do we find what this is? Instead of taking g of 2 and getting a number, we have to go backwards and figure out what would give us 2. How do we do that?
So we go to like the 2 prime, like the 2 prime or g prime x wherever it equals 2 and find where it equals that.
Right, but not g prime because right now we're just on the regular one.
Oh, so just be g.
Yep. So
So
where does
that'd be 1.
boom? So that's that. Love it. And now we don't have to, we do have to still go backwards a little bit, but we actually already did part of our problem here. Same thing for this. So we got to plug 2 into this formula right here, but g inverse of 2 we already said was 1.
Yeah,
right?
it's 1.
And then what's g prime of 1?
G prime of 1 is 5.
Right, so this is 1 over 5, and that's the slope. And then can you write the equation of the tangent line from there?
Yeah, it'd be y minus 1 equals 1 over 5 x x minus, or just 1 over, oh yeah, 1 over 5 then the x minus 2.
Perfect. Yeah,